Okay. Does anybody have any problem before we continue with 3.1? Last time we started linear models in this section, we didn't finish it. So we just try to model real world problems by linear differential equations in first order and solve it. So we discussed several examples. Essentially, we talked about the population growth, the problem for internet all the time. I don't know why. Let's see. So today we just continue with linear models. So the first topic or example is called Newton's law of cooling and warming, which we already introduced in chapter 1, I think, about this problem. So essentially, you have an object and you put in the environment with the temperature Tm. So you want to know how the temperature of the object changes. So eventually we know the temperature of the object will be the same as the environment, but how the change happens. And it turns out the temperature change is governed by the first order differential equation of the capital T over dt equals k times capital T minus capital Tm, where capital T is the object of the temperature of the object, and the small t is the time. So this applies to all the situations where you have some object with temperature initially different from the environment. Okay. So we can solve this problem easily if we rewrite this differential equation as the capital T minus capital Tm over capital T minus capital Tm equals k times d small t. Okay, so I have divided by capital T minus capital Tm on both sides of the equation and multiplied d small t. But also I have rewritten d capital T by d capital T minus capital Tm, because capital Tm is a constant. So there's no problem we do that. And the reason I'm doing that is now we can integrate on both sides easily to find the solution of the equation. So when you do that, we're going to get the natural log of absolute value of capital T minus capital Tm equals k times small t plus C1, where C1 is an arbitrary constant. Just as usual, we take the exponential with base e or natural exponential on both sides, and we got the absolute value of capital T minus capital Tm equals e to the k small t plus C1, and then this equation turns out to be capital T minus capital Tm equals plus or minus e to the k small t plus C1. All right. You don't want the absolute value sign for the solution. So then you can break up the right hand side in the exponent, the sum into two parts, two exponentials multiplied together. So that would be e to the c1 times e to the kd. But you can rename that plus or minus e to the c1 as some arbitrary constant c that can be either positive or negative. So that takes care of the plus or minus sign. Okay. In any initial value problem, you cannot take both plus and minus at the same time. It's either plus or minus in this solution. So we call this number C. So then you can move capital TM to the right to get the capital T equals capital TM plus some arbitrary constant C can which can be either positive or negative times e to the k small t. So that's the change of the temperature of the object as function of time small t. Okay, so let's do initial value problem or a real world problem. So in this example, it says a thermometer is removed from a room where the temperature is 70 degrees and is taken outside. Okay, so that's the object, the thermometer. Where the air temperature is 10 degrees. Okay, so we know the temperature outside and inside are different. After 1/2 minute, the thermometer is 50 degrees. So obviously, it was 70 degrees initially when it was removed from the room. It cools down. So it becomes 50 degrees after 1/2 minutes. So the question is, what is the reading of the thermometer at T equal to 1 minute? Does anybody have any questions? I'm going to mute, okay. So the other question is, how long will it take for the thermometer to reach 15 degrees? Okay, we know the thermometer will cool down to 10 degrees eventually, but how long will it take? That's the question. So let's just solve this initial value problem. We already got the solution of the differential equation, so we don't have to restart. We just write down the solution to the differential equation, which is T equals capital T equals capital Tm plus C times e to the k times small t, where capital Tm is 10 degrees. That's the outside temperature. So we also have the initial condition when the time is 0, the temperature is 70 degrees. Okay, so that's when the thermometer is removed from the inside to the outside. Okay, so now we can plug in those numbers. So 70 degrees for capital T, 10 for capital Tm, and 0 for small t. Okay, so plug in those numbers in the equation. We got 70 equals 10 plus c times e to the k times 0. And e to the k times 0 is 0. E to 0 is 1. And 70, you can subtract 10 from the right side, you get 60. So at the end, we got a c equal to 60. So that's the arbitrary constant. Okay. But we still have one thing to figure out. That's the k. Okay. We don't know what it is. We know it's a constant. So we have to use the condition of, 1/2 minutes later, the thermometer reads 50 degrees. All right. So that means when t equals half, that's the time, 1/2 minute. And then the temperature is 50 degrees. So just plug in 50 for capital T and half for small t. And then we know capital Tm is 10 and C is 60. Okay, then we can solve for K. So we got 50 equals 10 plus 60 times e to the K times half. Okay, once again, you just subtract 10 on both sides of the equation, you get 40. And then you divide by 60 on both sides, so you get 40 over 60 on the left, which can be reduced to 2/3 if you cancel 20, both on the top and at the bottom. That equals K, e to the K times half. So now you take natural log on both sides, you get natural log 2/3 equals K times half. So then multiply 2 on both sides, you get 2. K equals 2 times natural log over 2/3. So we fixed the K in this solution. So now then we can answer the questions in the problem. What is the reading of the thermometer at t equals 1 minute? So just plug in 1 for small t in this solution. So the temperature we try to find is just Tm, which is 10 plus C times e to the kd. C is 60. Again, K is 2 natural log with 2/3, and small t is 1. So plug in those numbers, and using a calculator, you'll find out the final answer will be 36.7 degrees. So that's the reading of the thermometer after 1 minute. The other question is, how long will it take for the thermometer to reach 15 degrees? So this time, we know the temperature is 15, we want to find the time. But once again, you just plug in those numbers. So capital T is 15, capital Tm is 10, C is 60, K is 2 times natural log with 2/3, and we want to solve for T from this equation. All right. So we got another equation, 15 equals 10 plus 60 times c to 2 natural log with 2/3 times t. So subtract 10 on both sides, we got 5 on the left. So that's equal to 60 times e to the 2, and then 2/3 times t. You can divide it by 60 on both sides. So we got 5 over 60 on the left, which can be reduced to 1 to 12 if you cancel 5 on the top and at the bottom. So 1/12 is equal to e to the 2 and then 2/3 times t. And then take the natural log on both sides. So we got natural log 1 over 12 equals 2 times ln 2/3 t. So just divide by 2 ln 2/3. We got this small t over the time equals ln 1/12 over 2 ln 2/3. If you use your calculator to figure out this number, it will be 3.06 minutes. So that's about 3 minutes. So it takes 3 minutes to cool down the thermometer to 15 degrees. Okay. So once again, the problem is not very complicated, but you have to, figure out these constants in the solution using the information in the problem. Okay, so that's the first example. Any questions about this problem? If not, let's just continue with the next example. So mixtures, okay. So that's another real world problem we discussed before. So, you have a tank with some solution. It has some input and it has some output with flow. And then they have different concentrations for the input as in a solution and the output solution or flow. So you want to solve for this problem. So how the concentration of the solution changes with time in the tank. But the basic equation we use, a rule, is dA over dt equals input rate of salt minus output rate of salt. Okay, here A is the amount of pure salt in the tank. Okay, so the rate of change of the amount of pure salt in the tank is equal to the input rate of pure salt minus the output rate of pure salt. Okay, so that's the physical law or the equation we start. So let's just solve one of those problems. So in this example, it says a tank contains 200 liters of fluid in which 30 grams of salt is dissolved. So that's the initial condition. Initially, the solution has 30 grams of salt. Brine containing 1 gram of salt per liter is then pumped into the tank at a rate of 4 liters per minute. So that's the input flow. All right. The well mixed solution is pumped out at the same rate. Okay, so that's the output rate, output flow. Find the number A of T of grams of salt in tank at time T. All right. So we just find out the input rate and output rate and set up equation, to solve. So first, what is the input rate of salt? You just multiply the concentration of the input solution times the flow rate. Okay. So it says 1 gram per liter. So that's the concentration of the input flow. And the 4 liters per minute is the actual flow input. So if we multiply the concentration and the flow rate, the input flow, you're going to get the 4 grams per minute. So you cancel the liters. So that's the input rate of pure salt. So there are 4 grams of pure salt inputting into the tank per minute, basically. Okay, then we need to calculate the output rate of salt. Okay. But we don't know the concentration of the fluid in the tank, which is outputting. Okay, the input flow concentration is given 1 gram per liter, but the output flow concentration, we don't know, but we can use the information in the problem to write it down. Okay, so we know A, capital A, is the amount of pure salt in the tank at any time. So if you divide A by the volume of the tank, 200, you're going to get the concentration of the solution in the tank at any time. Okay, the amount of pure salt divided by the volume of the solution gives you the concentration of the pure salt. So salt concentration of the fluid in the tank is A over 200 grams per liter. So then we can write down the output rate of salt, which is the concentration in the tank, A over 200, times 4 liters per minute. So again, the same rate is outputting from the tank. So then you can cancel the leader, and you can also cancel 4 from top and bottom. So at the end, you're gonna get A over 50 grams per minute. So that's the output rate of pure salt from the tank. So now we got the input rate and the output rate. We can set up the equation. So that'd be dA over dt equals 4 minus A over 50. Okay, we plug in this input rate and output rate. So then you can solve this problem in different ways. You can solve by using technique of linear differential equation, first order, or you can do it by separate equations like we did in here. So for example, you can factor out -1 over 50 from the right hand side to rewrite the equation as dA over dt equals -1 over 50 times 8 minus 200. If we do that, you can easily double check, this is the same as the original equation if you distribute in -1 over 50 on the right hand side, okay? And then you divide by A minus 200 on both sides and multiply dt at the same time. Then we just got a separate equation, dA over A minus 200 equals now -1 over 50 dt, and then you can integrate on both sides. But before you do that, you want to write the dA as dA minus 200. And that will not change the equation because when you take the derivative or differential constant, you get 0. But then that allows you to integrate on the left. So after the integration on both sides, you're going to get natural log of absolute value of A minus 200 equals -1 over 50 t plus c. Okay, where c is arbitrary constant. Okay, once again, take the natural expansion on both sides. You're going to get absolute value A minus 200 equals e to -1 over 50 t plus c. And the right hand side can be break up into two products as e to -1 over 50 t times e to the c, or we can call this e to the c as c1. So then we can take care of this absolute sign to write the solution as A minus 200 equals C2 e to -1 over 50 t. Okay. So C2 can be either positive or negative. All right. And then we use the initial condition to figure out this C2. Remember, initially, the tank contains 30 grams of salt. So when t equals 0, A equal to 30. Okay. So plug in 30 for A and 0 for t, we can find the C2. So again, e to the -1 over 50 times 0 is e to the 0, which is 1. So we got a C2 equals 30 minus 200, so that's -170. So the solution to the problem, the initial value problem will be A minus 200 times -170 times e to the -1 over 50 t. If we move 200 to the right-hand side, you got A equals 200 minus 170 times e to the -1 over 50 t. So that's the final answer for the problem. Any questions? So once again, the solution is not complicated, but you do need to, to find out input rate and output rate. Okay, before you even set up the different equation. To solve the equation is not very difficult. Okay, so this is usually true when you um, try to solve a real world problem. The mathematics may not be very difficult, but um, to set up the equation itself takes a little time. Okay, no question, then we just go to the next page. The final example is about a series circuit. Okay, so as we also discussed before, we have different types of series circuit. We can have a LR series circuit, inductance and resistance in the circuit. The equation or differential equation governing the flow of current is L times di over dt plus R times I equals e to the e of t, where L is the inductance of the inductor, R is the resistance of the resistor, I is the current, and E of t is the power. Okay. Similarly, in the RC series circuit, the differential equation will be R times I plus 1 over CQ equals E of t, where C is the capacitance of the capacitor. Q is the charge on the capacitor. But I is just the dq over dt. And the current is just the rate of change of the charge. So the equation then can be rewritten as R times dq over dt plus 1 over CQ equals E of dt. So this time the problem becomes solving Q instead of I. Okay. So if you major in electrical engineering, then you should be familiar with those equations. So let's just solve one example. A 30-volt electromotive force is applied to a AR series circuit in which the inductance is 0.1 Henry and the resistance is 50 ohms. Okay, so now this sentence gives a lot of information here. So 30 will be the ET on the right-hand side of the equation. So we know this is the LR series, so we use the first equation. So inductance L is 0.1 and resistance R is 50. Okay, so then we need to solve for current I from this equation. And the question is actually find the current I if I of 0 equal to 0. Okay, so that's the initial condition. And determine the current as t approaches infinity. So what eventually the current is, basically, it's asking that question. So just plug in those numbers. Again, as I said, 0.1 for L, 50 for R, and 30 for E. So we got 0.1 di over dt plus 50 times I equals 30. So you can multiply 10 on both sides of the equation to get the di over dt plus 500 I equals 300. So again, this equation can be solved in two different ways. You can solve it by using formulas for linear first-order differential equations, but also you can solve it by separate equations. So if you move 500 I to the right, it becomes negative. And then you just factor out negative 500 on the right side to rewrite the equation as di over dt equals negative 500 times I minus 0.6. Once again, you can easily double check the right-hand side by distribute the negative 500 on the right hand side, you should get the original equation. Okay. So then we can divide by I minus 0.6 and multiply dt to separate the variables. As always, you rewrite di on the top of the left hand side as di minus 1.6. Okay, then you can integrate on both sides. So if you do that, you can get the natural log or absolute value of I minus 0.6 equals negative 500 t time plus arbitrary constant c. So take the exponential on both sides. You can use another arbitrary constant, c1, instead of e to the c in here. But basically, when you take the exponential, the sum of the exponents becomes a product of two exponentials with same base e. Okay. So I minus 0.6 equals e to the negative 500 t times e to the c, or you can rewrite that as c1 if you want. Okay, actually we might should have done that. Okay, because I minus 0.6 can be either positive or negative. Okay, but if you do that, then you can use the initial condition to find out that arbitrary constant is c1. Okay, so at time t equal to 0, current I is 0. Okay, so then plug in 0 for I and 0 for t in the solution. We got minus 0.6 equals e to negative 500 times 0 times c1. Okay, you can use c1 instead of e to c in here. So 0 minus 0.6 is negative 0.6, and negative 500 times 0 is 0, e to 0 is 1. So we got the negative 0.6 equal to c1, the arbitrary constant. So then the solution of the original problem, initial value problem, is I minus 0.6 equals e to negative 500 t times c1, which is negative 0.6. Okay. So then you can move 0.6 to the right hand side to get the solution of the problem. I equals 0.6 minus 0.6 e to negative 500 t. Okay, so that's the solution to the initial value problem. So that's the first question. Find the current I of t. And then when you determine the current as t approaches infinity, so we need to see what happens when t becomes large. So remember, when t becomes large, you get the large negative number in the exponent of e. And then the limit of that will be 0. Okay. As t approaches infinity, e to negative 500 t approaches 0. So then eventually, the current I is approaching 0.6 minus 0.6 times 0. Okay. So 0.6 times 0 is just 0. So that's just 0.6. So eventually, the current is just 0.6 amperes. All right. And so that's a constant. So there is a transient period before the current stables. That is governed by this equation. Okay, so that's the solution to this problem. Any questions? If not, I'm going to stop the recording.